Hey everyone, let's talk about coupled reactions. When reactions are coupled together, what we mean is that we're using a thermodynamically favorable process to drive a process that would not be thermodynamically favorable. There's a couple of caveats to make this work. First, there has to be a common chemical species between the two equations. And secondly, you're going to find that this is really just an application of Hess's law using delta G. And so all of the rules for Hess's law apply. If we take a look at the example I have down below, zinc sulfide is one of the common ores that zinc is mined out of the earth as. And really, when we mine it, we want the metal. But if you just try to decompose zinc sulfide into its component elements of zinc and sulfur, delta G for this process is 198.3 kilojoules per mole. This is incredibly unfavorable. However, luckily for us, if you take that sulfur and then you further react it with oxygen gas, you can make sulfur dioxide. And that process has a delta G that is negative 300.1 kilojoules per mole. And so both steps taken as a sum can be expressed in the following way. If we add our chemical equations and then cancel any chemical species that are on both sides of the arrow, we find that overall we have zinc sulfide plus oxygen gas makes zinc plus sulfur dioxide. And the value for delta G naught for this process, now that it has been coupled, is negative 101.8 kilojoules. Quick reminder that that negative 101.8 kilojoules is for the reaction as written, so 1 mole of all of our chemicals, but now it's thermodynamically favorable. Recognize that really what we're doing is we're leveraging Le Chatelier's principle here. If we make sulfur and then we continuously use it up, then the reaction, that first reaction, is going to continually produce more product because it cannot reach equilibrium. This same idea of coupling reactions has a huge impact biologically. Virtually every reaction that occurs within the metabolic processes is coupled to the hydrolysis of ATP because those reactions are not thermodynamically favorable. So if you consider taking glucose and breaking it down into energy during glycolysis, the first step in that process requires you to take glucose and add a phosphate, making the chemical glucose 6-phosphate and water as a byproduct. Delta G for that process is 13.8 kilojoules. That is not favorable. And it's going to have an equilibrium constant that is right around 10 to the negative third. So you're going to end up with only one product for every 1,000 reactants. That's not going to be effective as a part of a key step within metabolism. So what your body does is it links it to the breakdown, the hydrolysis of ATP. So when you take ATP and you react it with water and you make ADP and phosphate, that process has a delta G of negative 30.5 kilojoules per mole. So taken as a whole, the overall process of glucose and ATP making the glucose 6-phosphate and ADP has a delta G of negative 16.7 kilojoules per mole. This is thermodynamically favorable. Again, if you take a look at your equilibrium constant for the overall reaction and that original reaction, and I'm going to remind you that the way we're doing this is the fact that delta G naught is equal to minus RT ln of K. If you take a look at your equilibrium constant for this first process, K is equal to 3.9 times 10 to the negative third. Whereas the coupled reaction has an equilibrium constant that is 8.2 times 10 to the second. So by coupling the reaction, we are now going to have several hundred times more product than we do have reactant, which then we can consume in future processes and further drive that reaction forward. So coupling reactions are incredibly, incredibly important in a variety of situations. So in sum, when it comes time to make a coupled reaction, you're using the same rules as Hess's law. Take your two reactions, manipulate them as necessary, add them up, see how you can improve your value for delta G, taking something that was a positive or non-thermodynamically favorable process and coupling it to a second reaction to come up with an overall thermodynamically favorable process.